in that context. And the next co-host speaker is on behalf of the Washington Evolutionary Systems Society and the group of people that have come to the Congress from this group. And the speaker is, excuse me, Dr. Jerry Chandler, who is in fact the president and a founding member of the Washington Evolutionary Systems Society. Like Professor Salthy, he was trained and spent many years as a biochemist, but then expanded the scope of his interests in retirement, he was for many years with the Institutes of Health and the Food and Drug Administration, but when he retired, he joined the George Mason University as a research professor at the Krasnow Institute for Advanced Study, where he has been working on problems related to the evolution of complex systems ever since. So it's with great pleasure that I welcome Jerry Chandler.
Thank you. Thank you, and good morning, everyone. I know it's getting close to coffee break, and I will try and expedite matters as quickly. Clearly, earlier speakers in the program, particularly Eric Chasson and Professor Machuana and others, have already addressed several of the topics that I had originally included in my lecture, so that allows me to get by very cheaply and to move through very quickly, or relatively quickly. As Peter was so kind to mention, I am a biochemist by training. I came to systems theory relatively later in my career. My interest in system theory originated in the notion of, particularly of drug design and the origins of health and disease. Health and disease are complex situations where one would like to make some prediction about the future course of events. And normally this is left to physicians. However, if one is involved in pharmacology or toxicology or public health, one would like to make broader range predictions. And the question is, how does this relate to the overall systems approach to life and to society and to culture, as these are moral and ethical problems as well as scientific problems. Now roughly 15 years ago, it became apparent to me that the philosophy of physics, which is often confused with the philosophy of science, was not an adequate basis to really describe the particulars of human health. Well, the substance of life certainly is material. The particulars of human health and our abilities to predict matters in the future are perhaps very remote from some of the substantive issues of the nature of material. So in this context, I set about to develop a more coherent view of, if you would, the nature of life in such a way that basic biochemical and genetic processes could be involved to construct the particulars for a particular patient or a particular set of circumstances, and yet still be consistent with the generalities of substance and matter. So the first slide because of the enormous complexity of living systems and higher order organizations, I'm going to start with a metaphorical view of the organization of nature. This is purely a metaphorical tree in the sense that I would just like to bring an image to your mind, an image that that can serve as a broad general view of interrelationships in natural systems. It's a metaphorical tree, but it's not really a mathematical tree because there are no roots to this tree. While many people believe in the Big Bang and other such theories, clearly these ideas are intimately intertwined with metaphysical notions, as well as the top of the tree, if you would, is also an open question mark, and the question is how well we can predict what is going on. So we have then a global view an externalist view in a certain sense, of the evolution of nature, or the emergence of natural systems, starting, for convenience, with the natural numbers located at the bottom, and with time, the emergence of more complex relationships, and particularly the emphasis is on relationships, that is, it's grounded in relational algebra. Therefore, in this context, we're concerned not only with sets of objects or the real numbers, but also with graphs and categories. On this side of the graph, of the metaphor, I have a list of numbers, which are various durations in time. No particular metric is associated with these. And corresponding in terms of to capture the essence of the nature of emergence, I have some symbols listed here as a notation, which should be interpreted as degrees of organization. Degrees of organization in this context is open in the sense that the only correspondence that's implied is some association with the ordering relationship of the natural numbers. This metaphor was constructed in order to provide a basis to bring the various aspects of science, whether it be particle physics, atomic physics, basic chemistry, biochemistry, cells, organisms, organs, cultures or societies. There's no limit on the number in terms of the notation, and the language is open. Therefore, one can use as much human creativity as one has at one's disposal to try and construct from this metaphor a coherent view of nature. The particular view that I will attempt to present today is that there's a certain coextensiveness between this metaphor and mathematical operations. And the particular mathematical operations of concern are those of addition, multiplication, and exponentiation. And I would point out that obviously conserved quantities basically are additive characteristics. Now, this metaphorical tree is not particularly unique. It's derived from the ideas of Desjardins, of Chance, of Eric Chasson, who was here, and others. And it's just an attempt to construct a mental image where we can place other ideas and concepts. The primary source for this view, of course, is Desjardins, originally written in 1938. He termed such matters as cosmogenesis, geogenesis, organogenesis, biogenesis, psychogenesis, technogenesis, and noogenesis. And certainly those were profound ideas at the time they were proposed. So to keep in mind what we're talking about, we'll leave this one up on this slide. Now, the question then becomes, if this is a notation grounded on the notion of degrees of organization, what do we mean by organization? In the sense of organization, I'm talking in terms of structure, and I'm particularly talking in terms of the structure of relationships. The origins of the word organization come from the same Greek origins as known for organic or organism. For me, the definition is a degree of organization, that is, one level in such a hierarchy. A degree of organization is a closure over relations among the matter, space, and time, and some sense of the stability of that. So each degree of organization has a category of observations, descriptions, and symbolizations. Thus, I quite agree with Professor Maturana's view on the notion of what needs to be conserved and how we view with the presence. With this definition, then, one can start applying language of science to the circumstances of a particular case. Being trained as an experimentalist, the question that first comes to mind is how does one relate what is out there in the external world, that which I interact with scientific activities. And I do say that I do view science as a human activity. So the fundamental notion that I use to try and bridge this gap thank you, Alicia, is the notion of a correspondence relationship. So there's an external world, I have my internal world, and according to Bertrand Russell, a correspondence relationship is the relationship between a fact and a belief. Particularly concerned about how we symbolize correspondence relationships, and the symbolization process is dependent on the nature of the scientific activity you're involved with. We have unique symbols for each degree of organization. So from this perspective of correspondence relations, human scientific activity can be viewed from a broad perspective of the capacity to observe, the capacity to symbolize, and the capacity to describe. And the question then becomes, if we want to transverse the hierarchical levels, how are observations at different levels related to our symbolizations at different levels, and our relation to our description at different levels. In traditional, particularly physics or particular interface between science and society, usually these distinctions are all collapsed into one, if you would, flat earth. There's one set of descriptions which attempt to describe complex systems. My own perspective is that this is insufficient for mathematics or for the mathematical descriptions of complex systems, and that we must maintain some hierarchy without specifically implying a particular causal relationship within that hierarchy, other than the historical one given. The next step is, so the question of how do we relate these three notions associated with correspondence relationships to something that we might call scientific truth. And scientific truth itself is almost a misnomer. One would prefer such words as consistency or reproducibility or other terms which relate to scientific activities. Nevertheless, I will use the word truth because it communicates in a certain way that the philosophers love to talk about. So there's three basic philosophies of truth. Excuse me, there's many philosophies of truth. I chose three which appear to me or have resonance with me in the sense that they relate to my scientific experiences. One of these is coherence, that is a large global view of the world. According to the theory, to say that a statement or a judgment is either true or false is to say that it either coheres or fails to cohere with a system of other statements that is a member of the system, et cetera, et cetera. So it's a certain sense of universal statement of claim about truth. Obviously, such a universal claim must include all particular claims. So thus, any universal claim about health would have to apply to the health of each and every individual that is sitting here. So it's very difficult to make scientific statements that about health that are indeed coherent in that universal sense. Correspondence truth is already said. Bertrand Russell, the truth that consists of some form of correspondence between belief and fact, and is widely used. I would point out that correspondence can be of two types. One, a simple matching of objects with symbols, such as I would match Eric with a symbol E, and I would match Alicia with a symbol A, or that sort of thing, where I capture a large domain, if you would, of behaviors or relations. The other possibility is that I have a specific ordering sequence, such as the natural numbers, 1, 2, 3, where the correspondence then is in that area. Most importantly for science is the correspondence between the natural numbers and the numbering of the atomic elements, where you have 1 for hydrogen, 2 for helium, 3 for lithium, etc., 6 for carbon, where this correspondence now is not in terms of, if you would, independence relation between that symbol and that behavior, but rather a group of a fuzzy symbol, if you would, for that particular element. Finally, the pragmatic or the empirical, which is well known. There's no distinction of meaning so fine so as to consist in anything but a possible difference in practice. And of course, this is the fundamental basis of experimentation, that we can make distinctions and explore those distinctions at the experimental level. So the next question then, how do we bring together these ideas, number one, about human scientific activity, and two, the nature of truth, or scientific truth. And I particularly would say that we'd like to bring this into a conceptual view that is consistent with the hierarchical tree. So if we want such a conceptual view, we can make a simple-minded plot. This is, again, very little more than a metaphor, but yet it provides a basis for relational algebras to be constructed upon this. So across the bottom we have degrees of organization plotted, going from very small components to much larger components. If we want to look at this from a philosophical basis, one of these components we can name the whole. The whole can be decomposed into components, subcomponents, et cetera, to any degree desired. And correspondingly, any whole is embedded in a surroundings. These surroundings I will call the equiment. They provide the home or the economy for the existence of the whole. And this existence of the whole then is dependent on the circumstances which surround it. So now we can replace this hierarchical tree with something that has a little more mathematical shine to it, in the sense that it provides some relationship to the basic human scientific activities. Now, to bring these together, again in a metaphorical sort of slide with some hand waving towards graph theory, we can look at a graph composed of the pragmatic correspondence and coherent truths, and that being part of my internal mental activity. And then I can relate that to the symbols, observations, and descriptions which compose human scientific activity, that relationships with the external world. The nice thing about this is that there is, in a certain sense, a one-to-one correspondence between the notion of empiricism or pragmatism and observations, between correspondence, truths, and symbols, and between overall coherence and our linguistic descriptions of scientific activity. So in this, if we would, metaphor, or based on somewhat on graph theory and our views about truth, one can view human scientific activity as a prism at how we look at the outside world. And this can then be consistently constructed along the way. So, 2 or 3 more slides. The question then is, how do we make this coextensive? I have started to construct a coextensive relationship between the metaphorical tree and the degrees of organization. I would now like to pursue that coextensiveness in terms of mathematical relations. Any living organism has a genetic system. And this genetic system the notion of genetics comes from the notion of genesis, the same root origin of the word, which is the same origin of the word for a generating function. And I'm concerned then about a generating function which will generate these degrees of organization in terms of the relations between the different degrees of organization. So in contrast to some of the other views expressed, to me, the essence of the problem of complexity is how do I move from one symbol set and description to the next symbol set and description on and upward. This is the essence, to me, of the problem of emergence. In order to give a preliminary note on how I am approaching this, consider then the notion of a generating function. This being a genetic system, this being the source of reference for the behavior of living systems. And I say source of reference in the sense that it is retrodictive to the present. How far retrodictive depends on the language you choose to describe the system. The basic notion still being, though, that the reference system is retrodictive to the present. In the present mode, or the indicative mode, things are happening in the present in the sense of Professor Maturana's notion of presence. And that these relationships, some of them at least, are conserved such that one achieves some set of preferences. So one has a relationship between the reference system, the inference system, and the preference system. For life to reproduce itself, obviously the preference system must come back to the reference system. That is, the genetic system reproduces itself to create a new organism. To put this into pictures, if this is the original organism, during growth, there's an addition of material from the ecomont, from the external world, that allows the organism to grow. This follows conservation laws. Conservation of mass, conservation of charge must be followed for the growth of an organism. So at the lower levels, the conservation laws certainly apply. And this must be followed for growth in terms of energy, in terms of nutrients, etc. The relations that are formed during growth are inductive relations based on the reference system. And I will not go into that further other than saying that chemistry is an inductive science in that sense. The reference system gives us the mathematical domain, which is composed of a family of relationships, a family of graphs in this case, actually a family of labeled graphs, more specifically a family of labeled asymmetric pseudographs that can describe the structure of a chemical compound. So the domain for us then is a family of graphs. The inductive relationships, obviously a family of directed graphs, and they lead to the codomain. So in this sense, we have at a certain, for normal growth processes, we have the additive relationship over the domain. Now, at the same time, growth in living systems is not merely additive, but it is a controlled and regulated growth in time by biochemical regulatory processes, higher order regulatory processes, outside influences, other levels of the hierarchy can certainly influence these additive processes. Now the influence comes through rate processes. That is, it comes through temporal processes. That is, the time domain of these influences act on the multiplicative characteristic of catalysis. So the material reference is expressed in terms of the graph, follows the conservation laws, and is additive in character. The temporal aspects basically involve catalysis or other forms of transformation, for example, interior-exterior transformations, and involve multiplicative relationships in time. To relate these two, obviously the mathematical underpinnings is that iteration of addition generates multiplication. That still does not explain reproduction. In order to reproduce, we have a function that goes from one organism to two organisms. Now this is, if you will, is outside the normal view of how mathematicians view, for example, topology, where everything is constrained to 0, 1, or typically everything is constrained to 0, 1 relations. So in order to go from 1 to 2, from parent to offspring, we must have some separability function. We must have some separability function that divides this whole, separates into two new independent wholes, which, excuse me, I shouldn't use the word independence, two wholes which both now contain the initial reference system, the initial genetic system, the initial source of the dynamics. This then, obviously, if we iterate this process, we go from 1 to 2, 2 to 4, 4 to 8, 4 to 8, 8 to 16, and so forth. Obviously, this is an exponential relationship. Okay, so during growth, we must have conservation laws followed and the additive processes. And these are coextensive with our views of mass, our views of chemistry and graph behavior of chemical graphs. Regulatory processes, whether they be interior, exterior, or combinations of interior and exterior, influence the time domain behavior and involve multiplicative relationships And finally, the separation of one organism into two, or one cell into two cells, must involve an exponential relationship. So in that context, we can now look at our metaphorical tree again and try and associate within this context, and I mean associate here in the sense of associative algebras or category theory, relationships that are occurring at the lower levels, which we might choose to list as subatomic particles, atoms, molecules, macromolecules, cells, organs, higher organisms such as human beings, or still higher organisms such as cultures, or higher degrees of organization such as culture, or the world as a system, or however one chooses. So within this context, clearly within this notation, at levels O1, O2, and O3, that is up through molecules, the conservation laws must apply, and they do indeed generate the open space which Professor Maturana spoke of. That is, their potential for future relationships becomes expansive as you collect a larger and larger family of graphs. At the macromolecular level, it also, as an object, follows the normal rules of conservation in the sense of mass and charge. In addition, for proteins at least, the catalytic properties enter in the time domain, the directed referential time domain of that particular organism, and give us the multiplicative relationships at this degree. Above this level, if we're dealing strictly with biological systems, then we get into more complex natures of exponentiation, exponential processes. These exponential processes must be based on the iteration of addition at the material level and the iteration of multiplication at the macromolecule level. And finally then, the iteration of the separability function, which generates two organisms from one. And in that context, how are we doing time? 1 minute? Okay. With that, I think I will say that the coextensibility of such a metaphorical tree with mathematical operations can be described in this context. This context for establishing relations among the symbols that we use can be made consistent through operations within relational algebras. At the heart of this construction of relations over such a metaphorical tree and such a notation will be combinatorics. These will be highly irregular combinatorics because of the nature of chemical valence. Nevertheless, the stability of such systems by appropriate choices of combinations can be demonstrated, and this indeed has been demonstrated, for example, in our now very detailed knowledge of both the genome and the chemical components of a simple organism such as E. coli. So thank you very much.